What we're going to look at is the E1 elimination of a tertiary alkyl halide. Now, typically, when you're using a tertiary alkyl halide and you're trying to do an E1 elimination, it goes 50-50 with an SM1 substitution. And if you want these to actually follow this SM1-E1 pathway, you would need to be using a solvent that is capable of hydrogen bonding. You don't want to have a potential species in there that has negative charge. That would favor the E2 mechanism. And since we're trying to show the E1 mechanism, you need to use an appropriate solvent, something neutral. They need to be something like water, but water is not soluble with the alkyl halide, so you'd be using something like an alcohol or an amine to make this happen. I'm going to use methanol to keep this very simple. But the first step in this reaction is the slow step of the mechanism, where you actually form the carbocation. Now, we've talked about leaving groups. Bromide is a decent leaving group. It's a very weak base, and it's a large atom, so it can be our leaving group. But this would be the slow step of this mechanism, and this would result in the formation of a carbocation. Now, bromide may just go right back and act as a nucleophile and add to this carbocation that you have formed. That's absolutely possible, and quite likely, actually. But if it doesn't, the only other option you have in solution is the solvent. Now, this solvent can be a nucleophile or a base, depending upon need. It's not a really great nucleophile. It's not a really great base either, and that's why it really does 50-50. With these tertiary carbocations. Now, what we're going to be doing is we're going to be showing the E1 elimination. Be aware that SM1 does occur, but when we're doing E1 elimination, you need to remove a hydrogen from one of the adjacent carbon atoms to the carbocation. Now, if this had been secondary, which usually doesn't go E1 at all, but if it was, you would be thinking about a potential shift, seeing if that were possible. But since it's tertiary, we're not going to be dealing with something like that. Anyway, as you can see, there are 8 different hydrogens on these adjacent carbon atoms. And according to Zaitsev's rule, you want to take a hydrogen from the carbon with the fewest number of hydrogens. And the reason you want to do that is because you would make a more stable alkene as a result of that. So we're going to show the oxygen picking up the hydrogen here. As that occurs, the carbon-hydrogen bond will break, and that pair of electrons will be used to make the carbon-carbon double bond. It may have also, as a minor product, removed a hydrogen from one of these 2 methyl groups, and you would have made a double bond here. So there are 2 different products that literally could be formed in this E1 mechanism. So the major product would look like this. These other 2 species I'm writing here are just your spectators, but they're here. That's the major product. And your minor product would be this gem disubstituted alkene. And you have the same 2 other products. But the major one is the major because it's more substituted than the minor.